And here we go. Okay, so once again, it does not work, and I don't know why. What's going on? Oh, I see. This is a flaky thing. Okay, so my collaborators are the same collaborators as last week. Mike Catanzaro, who's a former student of Vladimir and myself, who's now at Iowa State, and Vladimir, who is in the studio audience. So let me start talking about a bit of the history of all of this. So in 1845, in the year 1845, and in the year 1847, Gustav Kirchhoff developed a static theory of electricity, which I'm going to explain. And two theorems are attributed to him. One is called the network theorem. And the network theorem talks about the distribution of current in an electrical circuit, how current is distributed in an electrical circuit. And the other theorem that's attributed to him is the enumeration of spanning trees in a graph. So, so here, like the relationship between the two is the idea is that an electrical circuit is mathematically modeled by a graph in the sense of last week that we talked about. Okay, so here is a picture of Gustav Kirchhoff. He was born in 1824 and died in 1887. And so in 1845, he would have been 21 years old when he developed this work. And here's the front page of his paper. And it says, it's in German, so I guess I can translate. The title is over or on the going through. Durchgang means going through, which means the transmission of an electrical current through a plane, in particular through a kreisförmige, which I think means circular form, from studiosus Kirchhoff. Studiosus was an ancient term, like an archaic term for student. And then he goes on in the beginning to say, explain what he's going to describe. He talks about one directs a constant galvanic current through a metal plate. And then he says that so the electricity then will be in a definite way. The electricity will partition itself, will break up. And at the end of the first paragraph, he says, I will first hear the theoretical consideration, give the theoretical considerations, and then the experiment, to describe the experiment that I've done, right? So he actually does an experiment and has done an experiment to actually justify his theoretical assumptions. So this is science, right? But it's interesting because it's really math. So before I talk about what he did, I want to point out that Kirchhoff's work was about just a few years later overshadowed by Maxwell's dynamical theory of electromagnetism. Maxwell's was a dynamical theory in the sense it involved differential equations. Kirchhoff's was not dynamical. However, and it was sort of forgotten, his work. However, attention to his network theorem was revived by Hermann Weyl in 1923, who was the first to explain the relevance of the subject of combinatorial topology, which at that time was called analysis situs. And it was Weyl who basically brought the relevance of topology to studying these network problems, these problems of electrical circuits. So here's a picture of James Clerk Maxwell and Hermann Weyl. Okay, so in a later development in 1945, at the network problem was recast by Benno Ekman in terms of the then young subject of homology and cohomology. So, you know, this was a further development, and all subsequent developments in this area have like different, it sort of broke up into sort of a topological point of view and an algebraic point of view. So Ekman's great achievement, if you will, is that he explains how it falls under the rubric of what became known as Hodge theory, or in this case, combinatorial Hodge theory. Here's a picture of Benno Ekman. I actually saw him talk before in the 1980s. And he was an interesting man. He's a Swiss mathematician, and he was a student of the great Heinz Hopf. So let me point out, this is actually a very interesting remark. I didn't know this until a few days ago. Weil's work on the network problem was published in an obscure Mexican journal. It is one of only 2 papers that he wrote in Spanish. Now, Hermann Weil was a very famous mathematician of his age, and the question is why he chose to publish this work in Spanish in a Mexican journal. And in 1954, Ekman, the same Ekman on the previous slide, asked Weil at the Institute for Advanced Study why he did that. And I think it was at the Institute. And for a remarkable and unexpected answer at the end of this talk, I can explain why, if you ask me why that happened. But I give a reference to a bunch of essays that Ekman wrote near the end of his life. That it's actually kind of amazing why he published there, right? So this is like, I never would have expected this as an answer. Okay, so that's the more or less the end of the history. So let me point out one more thing, though, that Kirchhoff's results are really theorems that have to do with linear algebra. What's amazing is that Kirchhoff discovered those results before linear algebra was even invented. In fact, linear algebra was not really invented, or matrix algebra wasn't invented until 1858. So that was 11 years after Kirchhoff's second paper. And it was in a paper of Cayley where matrices and matrix notation was introduced. And Kirchhoff had no matrix notation whatsoever at his disposal. Yet you can look at his paper and you see the guy is like something of a genius, that he's able to do all of what he's doing, right? He doesn't have the tools, but he nevertheless is able to do it. So this, I just enhances my respect for him greatly, for his accomplishment. Okay, so today's goals are really twofold. I'm going to formulate Kirchhoff's theorems. Then I'm going to describe a variant, which is due to Catanzaro, Cherniak, and myself, in the presence of twisting by a line bundle. And twisting by a line bundle, it turns out one can interpret that as a physical phenomenon, as a kind of fluctuation where maybe the battery that's connected to your circuit is not pushing into the circuit constant current. Maybe the current is oscillating, the amount of voltage is oscillating. So that's what twisting probably has to do with. Okay, so those are the 2 things. And at the end, I'm going to give you a bit of an aftermath of this story, which I only learned a few days ago. Okay, so part 1 is the classical 19th century work. Okay, so let's go back to graphs. So suppose I have a finite connected undirected graph. So remember what that means. I have a set of vertices. It's going to be a finite set in this case. X1 is a set of edges, okay? And I have attaching data. And if you recall what X0 choose 2 refers to, it refers to the set of subsets of the vertices of cardinality precisely 2. Okay, and what does connected mean? Connected means any pair of vertices are connected by a sequence of edges in the graph. So a path of edges. So here's an example of a connected graph. Now my graphs are allowed to have multiple edges between any pair of vertices, but I've just drawn a graph that's what might be called a simple graph, where at most one edge is between any pair of vertices. This is just done out of convenience. It's harder for me to draw in tick Z rounded edges, although it's not that hard. I'm just lazy. Okay. So spanning trees, that's the main concept of today. A subgraph that is a collection of vertices and edges that form a graph itself is a spanning tree inside X. is a spanning tree. If it's a tree, that means every pair of vertices is not only joined by a path, but by a unique non-backtracking path, right? So it's joined by a unique path. And the vertices, the spanning part of this definition is that the vertices of T and X coincide. So T contains all the vertices of X. So that's a spanning tree. And that's the most important definition you're going to have today. Here's an example of a spanning tree. So my graph is the same as the graph before. The dotted edges are in the original graph, and the orange edges are in the spanning tree itself. And this obviously forms a spanning tree. It contains all the vertices, obviously, and any pair of vertices is joined by a sequence of edges connecting the first vertex to the second vertex. Okay, so that's a spanning tree.
Question.
Yes?
Does a spanning tree have the property where if you join any other edge to it, it'll create a loop?
Yes. That's
Okay.
that's going to appear today as well. Okay, in the talk. Okay, so that's a crucial thing, right? Actually. So now there are other spanning trees. It's not a unique one in a graph. Here's another spanning tree in the same graph, right? You have this one and you have this one. There are even more, right? So it's not a unique thing. But the first question you might say is, do they exist in a graph? Well, let X be a finite connected graph, then X has a spanning tree. That's the first lemma. And the number of spanning trees in X is finite. This is an easy lemma to prove. How do you prove it? You select any edge from the graph, X, any one at all. If removing it results in a disconnected graph, that is a graph in which you cannot join vertices necessarily, then we put the edge back. We leave it alone. If not, we throw away that edge we removed. And we repeat this over and over until we can go no further. And the remaining subgraph is then obviously a spanning tree if you think about it for about 10 seconds. So this is how to construct a spanning tree. And there are even algorithms which enable you to do this quite algorithmically. That is, you can choose a cost function on the set of edges where you give each edge a different monetary value, and then you remove the most costly edges first, right? To see, and proceed in this way. Then there are only finitely many subgraphs of X. That means there have to be only finitely many spanning trees. By the way, this is not the only proof that there are spanning trees and there are only finitely many. Well, that there are spanning trees. There are other proofs, but this is the most conceptual one, and this is actually the proof that actually Kirchhoff uses in his monograph. He actually never uses the term spanning tree, but he talks about removing edges. And the result of which is this thing which we call a spanning tree. Any questions? Okay, so now the graph Laplacian came up last week. It's a matrix with entries indexed by pairs of vertices. And if you recall last week's talk, it was given by the matrix entries are given as follows. The diagonal entries are given by the degree of the vertex. That is the number of edges which meet at that vertex. And then if you're off a diagonal entry, if you're at I and j, you look at the number of edges which connect I to j directly. And then you take its negative, and that's the off diagonal entry. Right? Here's an example of a graph Laplacian of an undirected graph. So what you do, let's look at the graph, the vertex labeled 2. The vertex labeled 2 has 3 edges connected to it. And that's, you see the entry in the second row, second column of my matrix has a 3. That's referring to the number of bonds at 2. And then the other entries correspond to edges. So for example, there's an edge from 2 to 4. Therefore, the entry 2, 4 or 4, 2, it's a symmetrical graph, a symmetric matrix has an entry of -1. There is no edge from 2 to 5, and therefore the entry 2, 5 must be 0, and so on. So that's the graph Laplacian. And there are 7 vertices. This should be a 7 by 7 matrix, which it is. Any questions? So this is like an important thing to introduce also in my talk, the graph Laplacian. Okay, here's a lemma, properties of the graph Laplacian, which follow from elementary linear algebra. Number 1 is all the eigenvalues are real numbers and non-negative. Number 2 is 0 is always an eigenvalue of the graph Laplacian. And the third thing, which is probably the hardest thing to prove of all 3, is that 0 has multiplicity 1 as an eigenvalue. Okay, so that follows from the graph being connected, this last statement. Okay, so how do you prove the first statement that the eigenvalues are real and non-negative? That's easy. Since the Laplacian is symmetric, every eigenvalue is real. A symmetric matrix always has real eigenvalues. But why are they non-negative? Well, we'll see in the proof of part 3, that the Laplacian can be written as a product of matrices, non-square matrices, for a suitable matrix. I'll call it boundary with transpose boundary star. So if we just assume that statement, we're going to prove that in a moment, then it follows almost immediately. So let V be an eigenvalue vector with eigenvalue lambda. So then by definition of eigenvalue, so we're going to give then the scalar product of lambda V with V is given, or the inner product of lambda V with V is given by lambda times the norm of V squared by definition. But since V is an eigenvalue with eigenvalue lambda, that's the same as the scalar product of the Laplacian applied to V with V, which by what I prove in 3 below is boundary star of V, comma V inner product. And then using the properties of the transpose, that's the same as boundary star of V, inner product boundary star of V, which is the norm squared of the boundary star of V. So now the right-hand side of this equation is non-negative. Therefore, lambda must be greater than or equal to 0, because norm squared of V is also non-negative. So there you go. So lambda is always greater than or equal to 0. That's what we had to prove. And that's modulo the assumption that the Laplacian, which is I also call nabla, can be written in this particular way. So the proof of 2 is that 0 is an eigenvalue is extremely easy. Let 1 be the function, which is identically 1 on every vertex. So that's think of that as a column vector, which has 1 in every entry, right? So the reason why nabla of 1 is 0 is because of the way the Laplacian is defined. The entries in every row add up to 0 in the Laplacian, because the diagonal entry is the sum of the entries in all the other entries in any given row. So that's why 1. So this vector 1, boldface 1, is an eigenvector with eigenvalue 0. So now we get to the hard part, which is, it's not so hard. I want to claim that we can write nabla as boundary star, where the matrix entries are given by pairs consisting of a vertex and an edge, right? So that's those are the matrix entries. To obtain the decomposition, choose any set of directions on the edges, making X into a directed graph. And from now on, X will be directed once I've done this. For the rest of the talk, I'm assuming X is a directed graph. And the attaching data of that directed graph is given by this attaching map, which now assigns to an edge its ordered pair of vertices as endpoints. And then we're going to set this boundary of alpha equal to the initial vertex of the edge minus the terminal vertex of the edge, right? We take the difference. And that is, that's my matrix entry. And then, so in other words, that would be a column vector where all entries are 0 except that given by the vertex, which the initial vertex of alpha and the terminal vertex of alpha, where you have a 1 in the first case and a -1 in the second case. And then elementary linear algebra, which I won't do, you can do this yourself, it won't take you long. If you know your linear algebra, says the kernel of the Laplacian is the same as the kernel of the transpose of this operator boundary. And that's the same as the co-kernel of the boundary operator. That's sort of a formal property, by the way, following from linear algebra. You actually learn this theorem in our 2000 level linear algebra class. You may not state it this way, but this is a statement that you do learn, and well, some version of it you do learn. Now, X is connected, and what does that mean? If you interpret what it means to be connected, and you look at the definition of the formula for the boundary operator, boundary of alpha, you see that, first of all, that if you have a pair of vertices which are connected by an edge, then they're in the image of the boundary operator, right? Because that edge has that boundary up to sign. And then more generally, if you have a sequence of two vertices which are connected by a sequence of edges, then it's in the image of the boundary operator. And so therefore, the difference between any two vertices, I and j, is in the image of the boundary operator. And that's enough to conclude that the co-kernel of the boundary operator is equal to 1, right? So therefore, because of that, the kernel of the Laplacian has dimension 1. And that's what we needed to prove, because that shows the multiplicity is 1 of 0 as an eigenvalue. So that was the hardest part of this proof. Any questions? Okay, so this is really just classical linear algebra. There's nothing deep here. Okay, so now let me state the matrix tree theorem, the first statement of it that one might read when going to the literature. Suppose you look at all the non-zero, and there should be less than or equal to, there's a typo there for lambda 1 and lambda 2. So let's look at the set of non-zero eigenvalues of the Laplacian and take the product. Then that's equal to d times the t of x, where t of x is the number of spanning trees in x. So, and d is the number of eigenvalues of the matrix, including 0, right? So, so it's actually also the number of vertices. So d is the number of vertices of my graph. So in other words, the product of the eigenvalues, which is of the non-zero eigenvalues, is equal to the number of vertices times the number of spanning trees in X. Okay, so that's the matrix tree theorem. Okay, so I'm going to prove this, but before I prove this, I'm going to rephrase it, what this really says. So let's look at the inner product space spanned by the vertices of my graph. So that's a vector space whose basis is the set of vertices, and the set of vertices form an orthonormal basis. And now let's look at the boundary operator. The boundary operator can be viewed as a linear transformation from C1 of x to C0 of x. C1 of x is called the 1 chains, and C0 of x is called the 0 chains. That's just language. And a boundary is the map which sends an edge alpha is on a basis element to d0 of alpha minus d1 of alpha, the difference between the endpoints of alpha. So Ci of x is the space of I chains. I just said that. And now I'm going to introduce some new terminology. B0 of x is the image of the boundary operator. That's the space of 0 boundaries. Z1 of x is called, which is the kernel of the boundary operator, is the space of 1 cycles. And one more thing which is related to all of this is we have the homology of the graph, which is hi of x, which is the, if I equals 0, we take the co-kernel of the boundary operator. So remember, that would be C0 of x, where we quotient out the boundaries, B0 of x. And H1 of x is the kernel of the boundary operator. In other words, that's another name for the 1 cycles. Turns out that the calculation I did in part 3 of my proof of the lemma shows that the dimension of H0 of X, the zeroth homology, is the same as the number of connected components of my graph, which is 1 in our case, because we're assuming the graph is connected. Every pair of points is joined by a path. And there's another thing I can introduce here, which I'll never use in the, I'll barely use it in the talk, the Euler characteristic of the graph, which is defined to be the number of vertices minus the number of edges. Turns out by elementary linear algebra is the same as the dimension of H0 of X, which is called the zeroth Betti number, minus the dimension of H1 of X, which is called the first Betti number, right? So you get this thing called the Euler characteristic. It can be expressed in two different ways. And this is actually an important thing. And this can be greatly generalized to other spaces, but we're just talking about graphs today. Any questions about the definition? Okay. So here is a homological characterization of spanning trees. A subgraph of X is a spanning tree. Well, you need all the vertices. H1 of T, the first homology of T, is 0. That means there are no one cycles. There are no one cycles. And the map from H0 of T to H0 of X is an isomorphism. I'm expressing this in a funky way because it really we could have just said that the dimension of H0 of T is 1 or T is connected. That's equivalent because we're assuming X is connected. But let's express it this way because in the second part of my talk, I need this more general formulation. Okay, so this is another way to characterize a spanning tree. And I'm not going to prove this lemma. It's easy enough to prove. Okay, so I want to consider now the restricted Laplacian. So instead of looking, so the restricted Laplacian can be viewed as the following thing. So you start off with your zero boundaries, you apply the transpose of the boundary operator to land you in the one chains, and then apply the boundary operator to land you back in the zero chain. So it's the matrix multiplication boundary, boundary star, but it's acting on the zero boundaries rather than the zero chains. So it's called the restricted Laplacian. And now it turns out that this is an isomorphism by construction. And the matrix tree theorem is equivalent to the following assertion. It's actually, now I don't have to talk about eigenvalues. I just say the determinant of the restricted Laplacian is the number of vertices times the number of spanning trees. And this is a very convenient form of the matrix tree theorem. And I think we may be even like one of the few people to state it that way. I'm not sure. Well, not many people state it this way, but this is our preferred way of stating it. Okay, so now let's go to the network theorem, which is kind of most of my talk in a way. So an electrical network consists of wires and nodes, which has current flowing through it. So the 19th century is a very interesting time in the history of science because it was the first time electricity was studied as a scientific phenomenon. Before that, it was just an oddity. And so they were very early. My father, when I was growing up, had a book on chemistry, and only 8 of the elements were known that we talk about today. 8 elements on the periodic table were known at the time. And my father had this book in 1809 written by Faraday, believe it or not, right? Michael Faraday, the great Michael Faraday. And so when he died, I looked for the book in his collection. He had a very large book collection and somebody stole it. And I was very upset because I really wanted to inherit that book. Anyway, very little was known about electricity in the early 19th century. There was Faraday, and then there was Humphrey Davy, and Ohm. And the earliest known law might be Ohm's law, which says that voltage is resistance times current. I'm using J for current or impedance. Usually in the English word, we use I for current, but I'm using J because some of the literature, classical literature, uses J. Kirchhoff's voltage law which Kirchhoff discovered, introduced in his 1845 paper, is that the algebraic sum of voltages around a cycle in the circuit is zero. You go around the circuit, in a circuit around a cycle in the circuit. That means you move in a path that returns to itself in the circuit. The algebraic sum of the voltages is zero. And I'll depict that on the next slide. And then there's the current law in the same paper, which is the algebraic sum of currents leaving or entering a node is zero. So that's the current law. Incidentally, the current law is usually known as Kirchhoff's second law, and the voltage law is usually known as Kirchhoff's third law. I'm reversing it here because in the 1845 paper, it's listed in this way. He changed it in the 1847 paper, but the voltage law is conceptually more simple. And that's why I'm also including it in this order. So here's here we go. For some reason, I'm going to try to fix this. Oops. I have this problem that it locks up. I don't know why. Okay, so the main problem of network theory is given an external voltage source like a battery, find the current and voltage along each branch of the circuit. That's really what the main problem is of circuit theory. So here are two pictures of the voltage law and the current law. Suppose this is part of my circuit where I go around, and the voltages are forces, they have directions. So they could be moving along the different wires in different directions. And so Kirchhoff says, suppose we wander around this square counterclockwise. Then you want V1 has a negative direction on it. So it's, V1 minus V, I'm going clockwise, it looks like. V1 minus V2 plus V3 plus V4 has to add to zero. And then in the current law, we look at the amount of current coming in, which in this case is the only current coming into the vertex in the middle is J1. And that could be equal to the sum of the currents going out. I think this is written incorrectly. It should be minus J. Okay, dog. I wrote this incorrectly. I'll correct it later on my slides. It should be J1 minus J2 minus J3 minus J4 equals zero, or J1 equals J2 plus J3 plus J4. So that's a typo, and I apologize for that. Okay, so the amount of current coming in is equal to the amount of current going out. Okay, so now resistance in this situation, when we try to abstract it into graph theory, is just a function on the set of edges. Any non-negative, any positive valued function on the set of edges is resistance. So each wire could have a different resistance. And now here's how to formulate the network problem mathematically. So we are given some zero boundary in the graph, right? Something in the image of the boundary operator. And this is called a node current or a terminal current. And this is from some external source. This is like voltage from an external source. And a solution to the problem consists of one-dimensional chains, that is a linear combination of edges called V, voltage and current, satisfying, first of all, Ohm's law. That is, the voltage is a scalar multiple by the resistance of the current, right? So that's the Ohm's law. The voltage law says this. Remember that the space of one chains, the vector space of one chains has an inner product structure, making the basis into an orthonormal basis. The basis is the set of edges. Suppose I choose for any one cycle in the graph, that is something whose boundary vanishes, I want the scalar product of it with the voltage to vanish. So that's the voltage law. And then finally, we have the current law, which says that the boundary applied to my current is equal to the given initial condition given by my node current. So the boundary of J must be P. Okay, that's what it's saying. So these are the three rules. Now, notice that given Ohm's law, if we could just find J such that R times J satisfies the voltage law and J satisfies the current law, we're done. So the whole problem is reduced to, finding J with the suitable properties. So let me explain, first of all, why this is like equivalent. So the voltage law says that V vanishes along cycles in the graph. The current law is really a generalization of slight generalization of what Kirchhoff did, because we're going to take P equal to K minus J, where J and K are vertices. That's in the image of the boundary operator. We saw in the proof of my first lemma that K minus J is a boundary of something. And what this should be interpreted as is that current flows into the circuit at node J and out at node K. So then for I not equal to J or K, for any vertex not equal to those two nodes, here's what's true. We can look at the inner product of J with the transpose boundary star applied to I, and then by the formal properties of the adjoint or transpose, that's the same as the boundary of J applied to I, but the boundary of J is supposed to be P, and P applied to I, the inner product of P with I is the inner product of K minus J with I, but if I is neither a K or J, its inner product with P is 0. So that's where the current law comes from. Well, not quite. I have to tell you why, what this has to do with the current law itself. Boundary star of I is the algebraic sum of the edges which meet I, because what is boundary star of I, inner product with an edge alpha? Well, it's the same as I, inner product with the boundary of alpha, but that's equal to 0 if alpha is not an edge which meets I, and it's equal to plus or minus 1 if it is an edge which meets I. The sign according to as to whether I is the terminus or the initial point of the edge, right? The initial vertex of the edge. And that means that boundary star of I is a linear combination with plus or minus 1s as the coefficients of all the edges meeting the vertex I. That's what it means. And that's the algebraic sum of the edges which meet I. So that's why the current law makes sense here. Here's a picture of a network problem where we have these external, we think of these vertices J and K as being external nodes. And when we take the inner product, when we check the current law, we're checking it at all the nodes, the vertices, which are depicted with small circles. Come on, dogs, go away. Okay, so here's a lemma, which is not Kirchhoff's network theorem. It just says any network problem has an abstract solution, and that abstract solution is unique. It's not a concrete result, it's an existence result, an existence and uniqueness result. It's very easy to prove. Here's a proof. Let's define a new inner product using the resistances. So what I'm going to do is I'm going to take the edges, which are basis elements. Let's take a 30-second break because the dogs, the mailman is here. It's okay. Okay. Okay, go inside. Go inside. Go inside. Go over there. Good dog. Okay, so let's define a new inner product. Where on basis elements, I have to tell you what it does on basis elements, and then you extend linearly. So if you have a pair of edges, it's going to be, and they're not the same, it's going to be 0. And if they are the same, you apply the resistance to it, and that's the value. So you no longer have an orthonormal basis. You have just an orthogonal basis, right? It's not normal because edges don't have length 1 anymore. And then let's take the orthogonal decomposition of the one chains by the cycles and the perpendicular subspace to the cycles. Okay, so the cycles, remember, the one cycles are the kernel to the boundary operator. So then the boundary operator, this is just straight up linear algebra, is an isomorphism from the perpendicular to the one cycles to the zero boundaries. It's an isomorphism. So let's define the current to be the perpendicular to the one cycles, an element of the perpendicular subspace of the one cycles, so that its image is given by the given node current P that's given at the outset, right? So that's J. And now we have to just check that Kirchhoff's conditions are met. Well, let's set the voltage equal to R times J. So the Ohm law is automatically satisfied. And then let's consider what the current law would be here. So let's consider, the voltage law. The voltage law would say that V inner product with a cycle is given by R times J inner product with the cycle, but that's the same as J inner product with the cycle in the modified inner product. But by definition, J and Z are orthogonal to each other in the modified inner product. So therefore it vanishes. So therefore the voltage law holds, and the current law holds by definition how we chose J. So we're done. So therefore we know there's a solution and it's unique. But really what we want is an explicit solution. So how do we get an explicit solution? Well, we actually chose this orthogonal, we have the orthogonal decomposition. So what we need to do is find an explicit formula for the orthogonal projection of the one chains onto the one cycles in this modified inner product. So the one cycles are a subspace of the one chains, and we have to project back, and we have to find a formula for that. Okay, so that's what we have to do. Okay. So this is in essence what Kirchhoff actually accomplished. Okay, so let me point out one more thing, which is this, before we prove it, we construct the proof. So there's something called conductance here. If you have a spanning tree, we could look at the set of edges on the spanning tree and take the reciprocal of the resistance, and that's called the conductance of the spanning tree, because conductance is like in inverse ratio to resistance, right? So we're taking like the product of the resistances along all the edges and then taking its reciprocal. And now once we're given the conductance, we can define a linear transformation which is going to give rise to our orthogonal projection, going from the one chains to the one cycles. And here's how it's defined, okay? It's called the fundamental cycle map. So what you do is T bar, so we're given a spanning tree, T, and we're going to define T bar of an edge to be the unique cycle of T union alpha, if alpha is an edge which is not in the spanning tree. And remember what Thomas said at the beginning of the lecture. He said, is T union alpha, is there a cycle in there? And the answer is yes, there's a unique cycle in there. And that we choose that unique cycle, and we define it to be 0 if alpha is an edge in the spanning tree. So that defines a function on edges, and you extend linearly. Here's a picture of the fundamental cycle map. Suppose alpha is this edge here in my graph X. Here's my spanning tree. So what do? I glue in alpha, that's in red. I look for the unique cycle, And how do I orient that cycle? I orient it in the same direction as alpha. Remember, alpha has a direction on it, right? So I move around the graph in that way. And then I ignore the rest of the spanning tree. So the red triangle is my fundamental cycle, right? I've just constructed a fundamental cycle for you. Okay, so here's the Kirchhoff network theorem. Here's the statement of it. The orthogonal projection of the one chains onto the one cycles in the modified inner product is the weighted sum of, so there's a normalization factor, which I'll mention at the end. You take the weighted sum of spanning of cycle maps, fundamental cycle maps, weighted by the conductance of the spanning tree. And then the prefactor, the thing that's in front of the summation, is the sum of all the conductances, that is each one conductance for each spanning tree that occurs in the graph. So it's a sum over spanning trees. Okay, so that's the statement of the theorem that, that was proved by Kirchhoff. And a spanning tree has, by the way, normalized conductance. We can take the conductance and divide by this prefactor that's listed here. I guess you would call it delta. And you can rewrite that as a product of resistances, because we've, where of the edges which are not in the spanning tree. And then the assignment, the function which assigns to a spanning tree its normalized conductance, is actually a probability distribution on the set of spanning trees. And this has actually given rise to an interesting literature in its own right, but I'm not going to talk about that here. Okay, so now we turn to the second part of my talk. And the second part of my talk is about twisted versions of the matrix tree theorem. So I want to talk about line bundles. A line bundle on a graph X is nothing more than a function which assigns to each edge an element of the unitary group of 1 by 1 matrices. If you don't like what U1, it's just a complex number whose norm is 1, a complex number of norm 1. So that's an element of the circle, in other words. So I want to talk about something called holonomy. So let's take an oriented cycle in my graph. So the holonomy of a cycle is you take the product of all, so an oriented cycle is a cycle in the graph that is a path which doesn't cross itself. It's a simple closed curve in my graph. So this is a sequence of edges which doesn't cross itself. And the orientation means that I'm either going around in one direction or the other direction around the cycle. There are only two directions I can move. So that an orientation is a choice of direction. So the holonomy of an oriented cycle is the product of the value of the line bundle on the edges of the cycle, but there's a sign plus or minus 1, so you have to invert it or take the complex conjugate according as to whether the direction of the edge agrees with the orientation of the cycle. That is, remember, the edges of my graph I've assumed to have directions, but that direction may not agree with the direction of my oriented cycle, the orientation. So I have to correct for that. So I take the product of all of these, and that's the holonomy. Now, if I define C bar to be C with reverse orientation, the holonomy behaves in the following way. It just changes by taking the complex conjugate. So here's a picture of a cycle in a graph. The cycle's in blue. Okay, now here's, I have to modify the holonomy in what follows. So let A be a subgraph having connected components A1 through AK, and assume the Euler characteristic of AI vanishes, okay? We talked about the Euler characteristic as being the difference between the number of vertices and the number of edges. Then it's by analysis of what the Euler characteristic is, it implies that each of these components has a unique cycle in it. Each component has a unique cycle. So consequently, A has a preferred set of cycles, one for each component of A. So let's assign an arbitrary orientation to each one of these cycles, and then define the modified holonomy of A to be, call it rho hat sub A, to be the following product. We take the product over all such cycles, one for each cycle, of 1 minus the holonomy of my cycle times 1 minus the conjugate of the holonomy of my cycle. Now, if you do elementary complex arithmetic, this is just twice the product over these cycles of 1 minus the real part of these cycles. So it's a real number, and it doesn't depend upon the choice of orientation, because if I replace each CI by its conjugate, it just reverses the order of the factors in the first product, right? That's all it does in the displayed first product. Okay, so now I wanted to find something called the twisted chain complex. So the twisted boundary operator is just the homomorphism, boundary sub rho, which looks like my boundary homomorphism that I defined before, and these are complex vector spaces now, I should have said, because I have a complex number here. So I now think of C1 as the complex vector space with basis given by the edges, and C0 is the complex vector space on the vertices, and then the twisted boundary operator incorporates into it. You multiply the initial vertex by the complex number provided by the value of the line bundle on the edge, and then take the difference with the other end of the edge. Here, Ci of x denotes the Hermitian inner product space with basis xi. So when I say Hermitian inner product space, I mean a complex vector space with a complex inner product. Okay, so when you reverse the order of the inner product, that changes the value of the inner product by a conjugation. Okay, so twisted homology is given by the same formula as homology, but I take the kernel in the co-kernel in degree 0 of the twisted boundary operator, and I take the kernel in degree 1. It's not hard to show that H0 of x, if x is connected, the twisted homology in degree 0 has dimension at most 1. But a more interesting feature of it is that the dimension is 0 if and only if the holonomy over any circuit of x is non-trivial, right? So H0 detects the holonomy over any circuit of my graph x. So here's an example of a computation of twisted homology. Here's a graph which is a triangle, vertices 0, 1, and 2. The value of my line bundle is 1 on the edges labeled 0, 2, and 1, 2, and it's given by some complex number zeta of norm 1 on the edge labeled by 0 and 1. So here's my basis, the edges and the vertices listed, and I compute the boundary operator directly, and this is what you get. It's a 3 by 3 matrix. And notice that the first column is zeta minus 1 because the value of the twisted boundary operator is given by zeta times the vertex labeled 1 minus 1 times the vertex labeled 0. And I'm using the ordered basis 0, 1, and 2. And the other columns are computed likewise, but the line bundle is trivial on those pieces. The determinant of this operator is zeta minus 1. So that determinant is going to be non-zero if zeta is not 1, and if the determinant is non-zero, then the homology vanishes because the homology is the kernel and the co-kernel, remember? So there's no homology if zeta is not 1, and there is homology in both degrees if zeta is equal to 1. So you can see you can get dramatically different homologies depending upon what you choose. Okay, so let's talk about twisted spanning trees. A twisted spanning tree is defined just like a spanning tree. So it's a subgraph, which contains all the vertices, but now H1 with twisted coefficients, with coefficients in the line bundle is 0. That means the kernel of that twisted boundary operator is 0. And lastly, H0, on H0, you get an isomorphism in twisted coefficients. So that's what a twisted spanning tree is. And I'm going to draw a picture of one in a moment. But here's an alternative description of a twisted spanning tree, which is more geometric. So let's assume H0 of the graph with twisted coefficients vanishes. Remember that H0 has dimension 1 or dimension 0. I'm assuming dimension 0 for the rest of the talk because dimension 1 is less interesting, it turns out. So then a subgraph is a twisted spanning tree if and only if it contains the vertices. Each connected component of T has trivial Euler characteristic, that is, it possesses a unique cycle, and the holonomia around each circuit of T, of each cycle of T, is non-trivial. I should have written cycle there, not circuit. Okay, so that's a characterization of a twisted spanning tree. And here's a picture. My graph is what is it? It's an 8x7 grid, it looks to me. The twisted spanning tree is the edges are in dark blue. There are 4 components, and each component has a unique cycle. I have not described the holonomy here. I've just drew a picture of something satisfying the first 2 conditions. So that's a twisted spanning tree. The twisted Laplacian is defined exactly the same way as the Laplacian. You take boundary times boundary transpose, but boundary now means the twisted boundary operator, and boundary, we take the conjugate transpose now because it's the adjoint operator. Okay, so conjugate transpose. And now we come to the twisted matrix tree theorem, which is due to us, which is due to Catanzaro, Cherniak, and Klein. Assume that the 0th homology of your graph vanishes. So that means all the holonomies over every cycle in the graph are non-zero. Then the determinant of the twisted Laplacian is a sum indexed over twisted spanning trees, and the sum is given a value, a weighted value for each spanning tree given by the modified holonomy of the twisted spanning tree. So that's the twisted matrix tree theorem that's due to us. A variant of this result was first due to Foreman and later reproduced by Kenyon, but it wasn't stated in this way, and their sum was a different sum. It was a larger sum. The result is stated as due to us. And this was proved in 2013. It appeared in 2013, this paper. Okay, so there's also twisted conductance. I'm now going to formulate the twisted network theorem. I should be done by 12:15, I think. So let's choose a resistance function on the set of edges as before. And the conductance is defined in the same way for a twisted spanning tree. I'm calling a twisted spanning tree a row spanning tree because it depends upon the line bundle. We take the product of the conductances along the edges, and then we put in a factor of the modified holonomy along the twisted spanning tree. So given a twisted spanning tree, we can define an analog of the fundamental cycle map, which is going to H1, which is the twisted cycles. It's called T bar again. I haven't changed the notation for that. And what you do is this. So if your edge lives in the twisted spanning tree, you assign it a value of 0. And if it's not, here's what you do. This is the interesting part. So you choose any non-zero vector in the first homology with twisted coefficients, right? With these line bundle coefficients. Now we know this first homology has dimension 1. It's non-zero and has dimension 1. So we choose any non-zero vector, any vector which spans that one-dimensional vector space, and then rescale that vector by dividing by the inner product of it with the vector alpha. So that normalizes it. And it turns out if you do it, what you get doesn't depend upon the choice of this non-zero vector C. Now this turns out to be, if you go back to the non-twisted case, this turns out to have been another way to define the fundamental cycle map in that situation. So this is this definition we're giving works in both cases. Okay, so we're just applying it to a different object that is a twisted spanning tree. A twisted spanning tree is not a spanning tree in the usual sense. Okay, and here's our theorem. The theorem is this: equip the one chains with complex, over the complex numbers with the modified Hermitian inner product, which is the obvious thing. Okay. Then the Hermitian projection of these one chains onto the one cycles, H1 of X twisted coefficients, is given by the same formula as you had in the non-twisted case. The same formula, except the objects you're summing over are different objects and the terms are defined differently because of these, because you have holonomy built into the answer. Okay, so let me remark about the proofs. A proof of the twisted network theorem, as well as the matrix tree, the twisted matrix tree theorem, appears in our paper, which I'm going to give you the reference at the end. And it closely parallels a proof of Kirchhoff's network theorem that appeared in 1961 in, of all places, the American Mathematical Monthly, which is something that was meant to be read by undergraduates, right? So it's really not a difficult proof, in other words, right? It's an elementary proof. Our proof is actually also quite elementary. The proof of the twisted matrix tree theorem also appears in our paper. In fact, we do something that no one else does. We deduce it directly from the twisted network theorem. And note the Kirchhoff theorem is most often proved using the so-called Cauchy-Binet theorem, which is a theorem of linear algebra. And our proof reduces the general case. The way we do it is we reduce the general case of X to that of the special case when X itself is a twisted spanning tree. And then we prove the theorem for a twisted spanning tree itself. But in that case, you just have to show the determinant of the twisted Laplacian is given by the modified holonomy of the twisted spanning tree itself. We deduce the latter identity using a mix of elementary algebraic topology and a perturbation method inspired by statistical mechanics. So that's what the method is actually kind of novel, I would say, from a traditional mathematical point of view. The approach appears to be new. Okay, so I'm in the home stretch of my talk. So what did Kirchhoff actually do? That's what I want to talk about now. What did he actually do? What he actually did, there's a paper that appeared in 2016 in some obscure journal called Croatica Chemica Acta, entitled What Kirchhoff Actually Did Concerning Spanning Trees and Electrical Networks and Its Relationship to Modern Graph Theoretical Work. And I just came across this paper within the last week. And its main conclusions are: Kirchhoff did define spanning trees. Kirchhoff did construct the fundamental cycles as I constructed them in my talk. He did prove the network theorem, but he was not interested at all in enumerating spanning trees and did not do so. right? So he didn't even formulate the matrix tree theorem. That's what this is. Matrix notation was first introduced in 1858. I mentioned that. The authors of this paper plausibly argue that had Kirchhoff had matrix notation, and had he been so inclined, he could have formulated the matrix tree theorem explicitly. There has been an abundance of myth-making in the last 100 or so years, maybe more, and it's not clear when the first unequivocal statement of the matrix tree theorem actually appeared in the literature. So it's not clear, right, when this theorem became a theorem in the literature. My own investigation, and I did a pretty thorough investigation, suggests that the first time this theorem appeared was in 1954, more than 100 years after Kirchhoff, in an article by Trent, by a mathematician by the name of Howard Trent, who incidentally only published 3 mathematical papers. So that may be the first place it ever appeared. It may have been known before that. It might have been folklore. So I'm just going to end this talk with the references. So there's our paper, which is called On Kirchhoff's Theorem with Coefficients in a Line Bundle, which appeared in 2013. There's this paper by Ekman, which is 13 short essays, which is available online, which goes into the reason why Hermann Weil's paper appeared in an obscure Mexican journal in 1923. There's the paper of Nerode and Schank in the American Mathematical Monthly, which gives a very elementary proof of Kirchhoff's network theorem. And then there's this paper I just mentioned on what Kirchhoff actually did. And then there's this paper by Trent, which appears in 1954. So I'm done. Are there any questions?
Yes, Professor, I have a question.
Hi.
Please, on the proof of the existence and uniqueness theorem.
Yes.
So we started by choosing a possible solution, choose a J such that V will be equal to RG.
Yeah.
And then proceeded to show it to satisfy the.
Yeah, let me go back to that slide first. So you said to go to the proof, right?
Yes.
Okay, 1 second. Okay, here's the, yeah. So, so what you do is you got to choose. So what we did was we chose, what did we do? We chose J, wait, that was the we have to go back to the existence proof. Sorry. So, yeah, so what did we do? We chose J so that boundary J is P. And the reason why you can find that J is the boundary operator is onto.
Okay.
Right, so there is a J whose boundary is P. But the point is the kernel of the boundary operator is the Z sub 1, the cycles. So you can always choose a J which lives in the orthogonal complement to the cycles whose boundary is P. And that's what we did there. So therefore, the current law is satisfied right away when you do that.
Okay, but this does not provide a concrete algorithm for.
No, this does not give you a concrete. This just shows you it exists, right? Okay, it shows you it exists. And as I didn't really show it was unique in the lemma, but you can follow the steps of the proof and you can see it must also be unique, right? It's not hard to see that, right, from the method of proof.
Okay.
Okay.
Yes, thank you, Professor.
Sure. Other questions, comments?
So still, what was the reason for Hermann Weil published the paper?
Oh, that's really interesting. I can, if you allow me to indulge you, or indulge myself, I should say, if you go to this paper, which I cited from Ekman, he actually says exactly why. So Ekman asked Hermann Weil in 1954 in the Institute for Advanced Study in Princeton. Why did you, well, let me just say this, okay? So somebody's interviewing Benno Ekman in the essays, I think. No, it's not. Okay, so here's how it goes. Why did you publish your 1923, 1924 papers on algebraic topology, Análisis Zitus Combinatorio in Spanish, in the Revista Matemática Hispánico-Americana, a periodical which was not well known and not easily acceptable at the time? Okay, so after his retirement from the Institute for Advanced Study, Hermann Weyl spent most of his time in Zurich. I had known him before in Princeton, and our context continued in Zurich. I asked him the above question in 1954 when he was just preparing. Oh, so he was in Zurich when he was asked this. When he was preparing his laudatio for the Fields Medals to be awarded to Serre and Kodaira at the International Congress in Amsterdam. So Weyl answered that he simply did not want to draw attention to those two publications. The colleagues should not read them. The field was not considered to be serious mathematics like the classical fields of analysis, algebra, and geometry. In the spirit of the modern term political correctness, it was at the early time not mathematically correct to work in such a field. But one has to recall that the medal was awarded to Serre for his famous thesis work on algebraic topology, homotopy groups of spheres. So in the meanwhile, in the 1950s, the field became respectable. So there's more I know about this. So if you go back to 1923, who was the most kind of important mathematician of his age that was alive? David Hilbert, right? Poincaré had died, I think, in 1912 or so, right? And Hilbert and Poincaré, when they were both alive, shared the distinction of being the most kind of prominent mathematicians of their era. But at this point, David Hilbert in 1923 was the most famous. And David Hilbert had this problem, these famous problems. In fact, I think there were 23 of his problems at the time, right? And of those 23 problems, not one of them is in the field of topology. Not a single one was in this field. David Hilbert thought that topology, which was then called analysis situs, was not a respectable discipline, right? And that is why that Weyl published the papers in some place that no one could find, right? That was the reason. I learned something else that you might like, Vladimir. So we talked about homology briefly in this lecture. So there's also something called cohomology, which was also kind of invented in the early 20th century. But the fact that the cohomology has what is called a ring structure, that it has a product structure, was not known in the early 20th century, except in the 1930s, it was actually invented by a Russian mathematician who is very well known, but not for anything in topology at all. Do you know who that was? Kolmogorov invented the product structure.
Yeah, but you know, why are you saying that Kolmogorov was not known in topology?
Because he really didn't publish papers in topology, right? He really didn't publish papers in topology, like non-algebraic topology anyway, right?
Okay. Because I was going actually to say Kolmogorov, believe me or not.
Yeah. So, but the fact is, so Ekman explains this in his essays, you know. So I thought that was also pretty fascinating to learn, right? So I guess like the takeaway from this lecture is, you know, I had this like wrong idea of the history of these ideas before I wrote this talk. And you can go back and look at like what actually happened. And it's a much more interesting story. And sometimes you get your own mathematical ideas by looking at the ideas these people had in the past. And I've actually had a lot of success in my career doing that. A lot of mathematicians don't do that at all, but I've had some success doing that. I can also tell you something else that's very interesting. It's extremely difficult to read papers in my subject that are written prior to 1943. 1943 is the seminal year where everything changes. So let me explain why. In 1943, you see like on the slide that I wrote down, the displayed boundary operator has an arrow. You see the arrow? So that arrow is part of notation for a function, right? For a map, right? Before 1943, no one did that, right? Everybody wrote down a function f of x, right? That's what they wrote down when they wrote down a function, right? So everything is written down in terms of formulas. Maps did not really exist in this particular way, right? Mappings, you know, A goes to B with an arrow were not written down at all. In 1941 and 1942, the beginning of World War II, kind of in the West, all the papers are written in this old language, this old notation. And then by 1943, there's a sudden change and everything is written differently. And you can really read it starting 1943. It's entirely different in the fields of algebra and topology, right? And this is due to the work of MacLean and Eilenberg almost at the beginning, but then it sort of becomes viral, right? Like almost like, you know, it's really becomes viral in the modern sense, you know, in the YouTube sense. And you know, within like 5 years, everybody's doing this in these fields. So I think that's also really interesting as well.
Hi, Dr. Klein. Is there a motivation behind the choice for the modified holonomy?
Well, my guess is yes. So you know the Kirchhoff spanning tree theorem, right? It's not a big leap to define twisted spanning tree once you have the axioms for spanning tree, right? And you have the notion of a line bundle, right? So you can say, let me compute in some special examples the determinant of the Laplacian of a very elementary twisted spanning tree, like a triangle would be a twisted spanning tree, right? A triangle satisfies the axioms for a twisted spanning tree, right? So let's calculate its Laplacian, its twisted Laplacian, its determinant. And you calculate it and you get exactly the modified holonomy appearing, right? That's where it comes from. So you just do an example and you see that's what pops up in the special case of a twisted spanning tree.
Okay.
Now, why does it have though these factors? Okay, so like that, what is it? Another reason why this happens is the following reason. Let me see if I can go back to this. See the first product that occurs. So why is there a row and a row bar? I can actually explain that. The row corresponds to the boundary operator. The 1 minus rho corresponds to something to do with the boundary operator, the twisted boundary operator, and the 1 minus rho bar arises because of its adjoint. It's, you know, the conjugate transpose. That's the reason, right?
Okay.
That's really probably a better answer to my question.
All right. That makes sense.
Okay. Other questions?
I can actually comment, you know, on twisting.
Go ahead.
So, you know, by this theorem, you see that, you know, it relates, you know, this twisted spanning trees to the twisted Laplacian. And the twisted Laplacian actually has a meaning in physics or like in random walk. So for example, as John explained at the previous lecture, if you look at the random walk on a graph, then you know, the Laplacian, the graph Laplacian, we will describe the evolutions of the distributions. So now, if you want to look at the random walk and you want to count, you know, how many times the system, you know, went through a certain cycle, then it can be naturally done by twisting the Laplacian. Mm-hmm. And these twisted these parameters, you know, in this holonomy, are actually that they have the meaning of the arguments of the generating function associated with the probability distributions of how many cycles you make over a long time.
So you're counting cycles in some
You're
way.
counting cycles
Right,
in a random walk, right?
right, right. That makes sense. Any other questions, comments? Okay, so again, if there's anything I can do better, please let me know. I hope this was at the right level, this talk was delivered at the right level. In a way, it was a more colloquium style talk, though. I didn't prove everything I stated, but I gave some ideas of the proofs. So I feel like I've done my job. I do highly recommend, by the way, these two papers. If you want to have some fun, like reading about history, which is this Ekman paper and this four author paper, and which is about what Kirchhoff actually did. You don't have to read the whole thing; just read the things that interest you. But it's actually fun to read. Okay, that was great. So I don't know what my talk next week will be, if I have one, but I'll know within a day or two. So take care.
Goodbye. Thank you.
Bye-bye.
Thank you.
Take care.
Bye.